Hi, and welcome to the Multi-Way Trees Lab. They are not very complicated, but let's first get into it. So basically, multi-way tree is similar to a binary tree. In binary trees, we had nodes which have left and right children. So each node can have at most 2 children. But for multi-way trees, each node can have more than 2 children. It can have at most n children. We can set it initially, and for example, this has at most 3 children for each node. All right. So a multi-way tree is basically a tree where each node can have multiple children. And in this lab, we're going to study 3 representations. In the first one, called the parent representation, for each node, we hold its parent. So we have a big array. And for each node, for node 1, we know that the parent is 2. For node 2, we know that the parent is 7. And so on. The only exception is node 7, which doesn't have any parent. So we put -1 instead of the parent. So this representation looks really simple. It actually is really simple, but it's hard to use because it's hard to find the children of 7, for example. To find the children of 7, you have to go through this whole array and see where we have 7. And as the declaration, it's only an array. So this is really simple. The second representation will be a little bit harder, but this is the most useful one. Because in this case, for each node, we'll keep an array of children. So for node 7, we'll know that it has children 2, 5, and 6. And we store the children as addresses, so we don't duplicate the information. We'll see how that looks like in a moment. In the main function, we'll only store the root. We'll only know the node 7, because from node 7, we can go everywhere else. And this is the most useful representation. I've seen this in practice a lot of times. All right, and let's see how it looks. So the data structure, for each node, we know a key. For example, here the key is 7. We have a number of children. So 7, for example, has 3 children and an array of children. So this will hold 2, 5, and 6. Here we can see the star, which means we're using pointers. And in the main function, to declare a node, we use again a pointer, and we only will keep track of the root of these 7. We don't care about the rest of the elements because we can get there from 7. And it actually looks like this. So each node has an address. And each node has a key, a number of children, and at most 3 children. Because we put here 3, we can put any number here, but 3 is enough for our case. So here we have node with key 1. So this element is actually this node. It has key 1, it has 0 children, and we don't care about this array. Question mark means we don't care. A more interesting example is node 7, which is at address 700. It has the key 7. It has 3 children. The nodes with address 200, which is 2, 500, this 5, and 600, which is the 6. So what's important here is that each node has an array of children. We also keep the number of children because we'll always have 3 slots here, so it will depend on the node itself. Okay, and the final representation is the binary. This one is a bit weird. And basically for each node, we will store its first children and its next siblings, so his brothers. For example, for 2, his first child is 1, and the next sibling is 5. This still means that 5 is a child of 7, but basically he is the brother of 2, so it's kind of indirect, but still a children of 7. All right. So the data structure looks like this. We have a key, the number from the node, and 2 pointers, one for the first child and one for the next sibling. And if we're trying to put some numbers in, it will look like this. So for example, the node with key 2 has the first child at address 100, which is node 1, this link, and the next sibling is 500, which should be 5. So we have key, first child, and next sibling. All right. Now let's look how to work with these representations. So let's see how it transforms from representation 1 to representation 2. Okay. So here we have the parents. Parent of 1 is 2, parent of 2 is 7, and so on. And we want to get, let's zoom out a bit. We want to get something like this. So we want to have nodes, and for each node to have an array of children. And the first step is to create an array, take an array of nodes, and allocate a node for each entry. So each cell in here, we want to be the address of one node. This should be the second node. This is the third node. Here we just do the setup. We allocate memory for our representation 2 nodes. Then we initialize our new nodes. So what we know that each node has the key, the index of the node. So node 1 has key 1. Node 2 should have key 2. Node 3 should have key 3, and so on. So we do this by using this line. For each I, we put the key equal to I. This should initialize the keys. And then we should set the number of children to 0 for each one of them, because initially all the nodes are lonely. They don't have any children. So this is the setup phase. We have the nodes, they are initialized, all good. Now let's see how we take this array, the parents, and put it in our nodes. So basically we take each pair, each entry from here with a for loop. So we look, the parent of 1 is 2. That means that at node 2, here on node 2, we should add one child, which is the first node. So here we put 100, the address of the first node. Next, the parent of 2 is 7. So we go to node 7 and add a child, which is node 2, 200. Then we take node 3, who has its parent 5. That means we go to 5 and add as a child 300. Now let's look at this one. The parent of 4 is 2. So we go to node 2 and add 4 as a child. So here we increase the number of children to 2 and add 400 here. Try a bit to think what happens here. So the parent of 5 is 7. Where should we add a child? If the parent of 5 is 7, we should go to node 7, 700, and add node 5, which is 500. Yep. And we go on and on until we finish the array. Be careful to do nothing for node -1, except saving it, because we should know that this is the root. We need to know the root for the next transformation. So be careful for -1. All right, if you have any questions, don't forget to tell me. Okay. Now, after you finish the first transformation, this one is a little tricky. So basically what we want is from an array of children, to transform to first child and next sibling. First child and next sibling. And the way we'll do it is to write a function called transform2, which takes as a parameter a node in representation 2 and returns a node in representation 3. So basically it will transform the node and all of its children in this representation. And let's start easy. The simplest case is if we only have one node. If the tree has only one node, if you want to transform it, so here the function takes a node in representation 2 with array of children, and it returns a node in representation 3, which has a first child and next sibling. But in this very simple case, it's quite easy. We just create a new node, create this new node, put in the new node the key of the original node, and if we only have one node, we can say that it doesn't have a first child and it doesn't have a next sibling. It's empty. And finally, we return the transformed node. So this is the skeleton on which we'll build the second transformation. We create a new node, put the key, and initialize the node. Now, the next step is, let's say our node has one child. So in representation 2, the array of children has one element, and the number of children is 1. 1 has one child, which is node 2. So here, when we want to transform it, again, when we transform node 1, we allocate node 1, we copy the key and initialize the rest, but we also check if the initial node had any children. If the initial node has children, the number of children is greater than 0, then in the result, the first child will be the first child of the initial node, but transformed with the same function. So if we want to transform node 1, it will also transform node 2 and put it as a first child. So then it will also allocate the node 2 and link it as the first child. Now, what happens when we have more than one child? Here, for example, we have 3 children. 2, 3, and 4. So again, we allocate a node, and then we see it has a child. I mean, at least one child. Then we transform the first child. We transform the 2. This one. Transform it and place it as the first child. So we make this connection. But then we also take the next node. So we skip node 0. I mean, no, the first child. We start from index 1 and take each one of these, the remaining children. Oh, oops, sorry, here should be J. And we transform also the other children. So here we will take node 3 and call transform 2 on it, and node 4 and call transform 2 on it. And this successfully transforms all of the nodes, but the issue is it doesn't make the connections. We should connect node 2 to node 3 and node 3 to node 4 using the next sibling. So the next step is to keep track of the last converted child. So here we start from node 2 when we convert to node 2. So this last will initially be 2200, the node 2. And we take each other child, so 3 and 4. We transform it, we transform this node into 3 and save it in variable v. So v is now this 3. And then we change the next sibling of the last one to the current node v. So here we go here and change the next sibling of node 2 to 3, like this. And also, now that we added node 3, we update the last variable to be node 3. Because next time we will want to connect 4 with 3. So next time we transform node 4, this node 4, into this node 4. We put the next sibling of 3 to be 4. We make this connection. And we update last to 4 in case we would have more children. But we don't, so that's it. So basically, for each node, we allocate a new node, transform its first child, and then transform the other children and link them to the previous one. If you have any questions, please let me know. If not, go ahead and try to implement it and see if any questions arise. All right. And after you finish, the final part is the pretty print, which looks kind of like this. So if you have a tree, a pretty print takes each node and it writes to the console, so you only see numbers and spaces here. But the basic idea is that nodes from the same level should be at on the same line in the output. So here it's clear that 7 is the root, and 7 has children 2, 5, and 6. And 2 has children 1, 4, and 9. So basically, pre-order is pretty print is something very similar to pre-order. So remember, pre-order for binary trees was something like this. So if we want to print a tree, we print the root, we print 7, and then we go recursively on the left side, and then on the right side. So here from 7, we go to 2, we print 2, then we go to left, we print 1, then we go to left, but left of 1 is null, so we don't do anything. Then we go to the right, which is also null, we don't do anything. Then we go to 9 and print 9. And we go back and print 6, 3, and 8. So basically the rule is root, then left, then right. Now, if you want this to be prettier, so you see 7 to 1, 7 to 1, 9, 6, 3, 8. So this one looks good, but the difference for pretty print is that we need some spacing. We need some nice spaces around. One thing that's quite obvious is that after each node, we want a new line. We want an enter key. So we print a new line after each node. And also, if we want the nodes on the same level to be on the same line in the output, we should print the same number of spaces for them. So 2 and 6, before them, before 2 and before 6, we should have the same number of spaces, the same space here. So this is level 0, this is level 1, and this is level 2. And at each node, we print its level spaces before it, so that we have them on the same line. It looks good. Here you can use a for from 0 to level and print, I don't know, 2 spaces for each one. But how do we know the level of each node? And the answer is, initially, when we start from the root, we use level 0 when we call the function. and we add it as a parameter. So each time we call recursively the function, we say that, well, when we print 7, the level is 0. But when we go to 2 and 6, we want level to be 1. And then when we go to 1 and 9, the level will increase by 1 again, and the level will be 2. So at each step, whenever we go to a child, we increase the level. And this should look correctly. And finally, for this lab, you don't have a binary tree like we discussed before, but we have a multi-way tree in the binary representation. So here, the two arrows aren't the left and right child, but they are the first sibling and the first child and the next sibling. So what will change here is these two lines. We won't go to left and right. We will go to the child, to the first child, and to the next sibling. Also, be careful in which order you want them to be. So do you want the first child before the next sibling, or the next sibling before the next child? And also look at the levels. So be careful. Do we need to increment the level to increase it by 1 when we go to the first child? What about the next sibling? Do we need to increase the level? I really hope this will help you, and also that you'll let me know if anything goes wrong. Good luck, and let me know if you have any questions. See ya.